Well, thank you for joining me for another Alex on Tech and Tech Advice Live video interview. I'm here today to get a special tour of Diraq. Now, I'm here with Andrew Dzurak. He's the CEO and founder, and Diraq is a quantum computing company, and we're here for the launch of the new commercial lab. So, Andrew, just tell us a little bit briefly about Diraq before we go inside and see some more.
Of course. Well, we founded Diraq in 2022, a couple of years ago. With venture funding, and we spun out of the University of New South Wales, where I'm a professor still, and where we had been developing quantum computing technology over the past 2 decades. So in 2022 we launched the company. The aim of Diraq is to deliver fully error-corrected large-scale quantum computing to the world, capable of solving problems like the design of pharmaceuticals, financial modelling, developing new catalysts in the chemical industry in order to reduce energy costs and energy consumption. To do that, we're developing quantum computers using very, very similar technology to the chips that we use in standard computers, and that we use in our iPhone or we use in our laptop. So the breakthrough that we developed here around about a decade ago was that we showed that we can modify a standard transistor called a MOSFET or a CMOS device, CMOS transistor. We showed that we could make that transistor operate as a quantum bit, which means that you can actually do quantum computing with it. And one of the beauties of this is that, as you know, I'm sure many of the people who are listening to this are very well aware, on a modern integrated circuit, we can have up to billions of transistors all operating perfectly. So the beauty of the Diraq design for our quantum computers is we use the same technology, and in fact we use the same chip manufacturing plants in order to make those chips.
That's actually revolutionary, because it's using modern processes to get quantum results.
Exactly right. And that's really been the conception of Diraq since, I've developed a range of patents over the previous decade. All of those patents are owned by Diraq outright now. We continue to develop a lot of new IP as we go along. So the great challenge in quantum computing is that in order to solve some of those problems I talked about, like drug design or developing new chemicals, catalysts, financial modelling, logistics, you need a quantum computer that can correct errors. Errors are quantum bits of information, are basically single electrons, single particles of light, single atoms. These are obviously very fragile objects. It's very easy for the information in them to get scrambled. So what we have to do is we need to put a large number of them together and perform error correction codes. And so it actually means that we need up to millions of qubits in order to solve those sort of problems I was talking about before. Now, there is a range of different technologies being explored around the world. For example, companies like IBM and Google are looking at superconducting qubits. There are a number of startup companies working on using trapped ions in vacuums, companies like IonQ in the United States or Quantinuum in the UK. And then we have companies that are looking at using photonic circuits, companies like PsiQuantum in the United States or Xanadu in Canada. And a number of others. So there are a range of different technologies, but all of those technologies, other than silicon, the actual quantum bits are physically much larger than a transistor. And so what that means is that when you go to millions of those quantum bits, the system actually becomes physically very large, and generally you need to actually cryogenically cool all of these systems down in order for the quantum effects to be preserved. So our competitor companies are developing technologies that require enormous amounts of cooling and additional infrastructure in order to make one computer. In contrast, because we can put everything on a single chip, it means that we just need one single refrigeration system. And the new lab that we've just opened has some of the refrigeration systems where we put our quantum chips, and so in one refrigerator we have an entire quantum computing system.
I mean, people would remember the football field-sized computers from the 1950s, and how we now have more power on our wrist Apple watches and Samsung watches than all those, a million of those computers put together. And that's what quantum computing for many people in the modern era was like. You went back to these giant computers, but and I have to say, look, this is the first time, even though you've been around working on this for a decade, and I've heard a lot about quantum launches. I mean, it's really great to see that this technology has been miniaturized, and clearly you're going to miniaturize it even further.
That's right. So
I want a quantum computer on my wrist. You know?
Well, the only challenge with that, the actual chip could go on your wrist.
Yeah.
Unfortunately, it's not so easy to put a refrigerator on your wrist.
You'll figure it out, though. I'm sure there'll be some way.
Well, it is possible to eventually miniaturize these things, but you know, at least for you know, the foreseeable future, we're looking at something that's more person-sized, a little bit like a refrigerator in your house.
But that is still, you know, an incredible advance.
And the intention is that we want to see hundreds or thousands of these quantum computers located in data centers.
Yeah.
Okay, and these quantum computers will interface with regular high-performance computing systems, potentially with classical AI systems as well, in order to enhance those and allow the solution of problems that can't be solved even with the most powerful AI or conventional supercomputing systems.
And how is quantum computing going to turbocharge AI and give it, you know, AGI qualities?
Well, there's no direct, clear-cut proof that will happen with quantum computing. There's a lot of work looking at quantum-enhanced artificial intelligence and machine learning. There are good prospects that it will provide capabilities that conventional, classical artificial intelligence isn't capable of. But at the moment, I wouldn't say there's any absolute clear-cut killer app that takes AI, you know, with respect to AI. The areas where we know quantum computers will have impacts that simply aren't possible even with AI or the most powerful supercomputings is in areas like drug design. So designing molecules that make up the pharmaceuticals and actually custom designing them in order to attack a specific virus or a specific bacteria. And the reason that can't be done on a conventional computer, even including artificial intelligence, is that the number of variables in those molecular systems in the calculation blows up exponentially with the number of atoms in the molecule.
Right.
And
it's just too much information.
That's right, in order to get the accurate description of these complex molecules. You can make approximate calculations, and that's what currently chemists do today when they're trying to do some molecular design, but these models break down once the molecules become very large, and this is where ultimately quantum computers will come into their own.
Now, we're going to hear a lot more tonight from the various speeches from the ministers and yourself and other investors. But what is the story behind the name? You were telling me it's quite fascinating.
Yeah, so it's named after Paul Dirac. So Paul Dirac was a British quantum scientist in the 1920s. He studied at Cambridge, and he was awarded the Nobel Prize in 1933 jointly with another physicist called Erwin Schrödinger.
Right.
Now you may have heard of Schrödinger's cat.
Everyone has, yeah.
Okay, so Schrödinger was the guy who came up with the idea of what's called a wave function, the fact that you can have what's called wave-particle duality, where particles can exist a little bit like waves. And he also, and related to Schrödinger, is the idea of the fact that until you actually measure something, it doesn't actually exist in that state.
Yeah.
That's the Schrödinger's cat paradox.
Yeah.
Now, what Dirac did, and he was doing his calculations at a very similar time to Schrödinger, he developed a completely different mathematical description of quantum mechanics. And in fact, the Dirac formalism is the most elegant and still currently used formalism that's used in quantum mechanics. So Dirac is really the guy who, in my view, was most influential in developing quantum theory. He also, interestingly, combined quantum theory with Einstein's special relativity, and he put the two equations together and derived a thing called the Dirac equation. Okay, and the Dirac equation predicted the existence of particles that people didn't even know exist, antiparticles, like the positron or the antiproton. This was all predicted out of Dirac's equation. But one other thing that naturally fell out of Dirac's equation was the prediction that electrons would not just have a charge, but also another property that we now call spin. And spin is related to the angular momentum of the electron
charge. Like a planet.
That's right. Yeah. That's right. You get angular momentum. And it turns out that when you put an electron in an external magnetic field pointing in one direction, the electron will always, when you measure it, either align or anti-align. This is the quantum nature of the electron. It has two options. Yeah. And when you measure it, you force it to choose one. And the way we use an electron as a quantum bit is that we put the electron into what's called a quantum superposition of up and down, or 0 and 1.
Yeah.
And so the electrons that we use sit inside these transistors that we've developed and that we're now making in chip foundries.
So it's just a happy coincidence that your surname and Diraq sounds very similar.
It is kind of a coincidence. Look, one of our investors wanted to call the company Dzurak with a Q,
Yep.
and I couldn't cope with the idea that I thought it was too egotistical.
Yeah.
But you know, I've always been a massive fan of Diraq, and I thought the name worked with the Q, so
Yeah.
that's where we went with it.
And so how long do you think it will be before people are able to go into their local computer store and buy a quantum computer to use for everyday work the same way we buy computers today?
I think that in terms of actually buying the hardware itself, that's going to be a long time, and it's like, I'm talking some decades.
Yeah.
But the way that most people will access quantum computers is just via the cloud.
Oh, yeah.
Right. So you will have the ability for certain apps, and these are probably apps that haven't even been designed at the moment, right?
Yeah.
So at the moment, most of the applications people are working on for quantum computing are the sorts of problems that big R&D companies were doing, like drug, pharmaceutical companies, big financial modelling firms, finance firms, logistics firms. Okay, so these are the sorts of things at the moment that high-performance computers would like to do but can't quite do. All right, that's the main near-term application. But look, I think there's a very famous quote from T.J. Watson, who founded IBM, and I can't remember the exact year that he said it, but he said, "I think one day there might be a market in the world for about 5 computers."
I remember that quote, yes.
And what that quote shows you is that when you create a revolutionary new technology, you can't predict how many possible applications can be created. So we already know a number of really important and economically important applications. I mean, the total revenue market predicted for quantum computing applications when we have a full error-corrected system is measured in the hundreds of billions of dollars.
Yeah.
That's the estimate. But that is just for the known applications.
Yeah.
Right. So it's inevitable that once people start playing with these, get more familiar with writing quantum algorithms, that completely new applications will come out. And we could well find that there are many apps in the future that we use on our phone that will be quantum enhanced.
Absolutely. Look, I always like to quote William Gibson, who wrote the Neuromancer novel. If you watch on Amazon Prime, the TV show The Peripheral, very smart, futuristic mind. And his quote was that the future has already been invented. It just hasn't been widely distributed yet. And these things take time to scale, and you've been living that for the past, I don't know, 10, 20 years. I mean,
that's right.
And making it all happen. So
that's right.
So just, we're going to have the tour, but just very briefly tell us what's happening tonight.
Right, so tonight we're opening the new laboratory that's right behind me. I'll show you a little bit about what we have inside there. So here on campus is where, as I mentioned, we developed a lot of the original intellectual property. We have, in a nearby building, very extensive laboratories where we make prototype qubits. We don't have a CMOS foundry on campus, obviously.
Not yet.
Well, I think we'll continue to do that offshore. And that's where those foundries are located, and it's a very significant. It's basically to build a foundry, you're talking about many tens of billions of dollars.
Yeah, absolutely.
Billions.
Yeah, billions. No, I mean, I don't know why we're not getting TSMC or Intel or these companies, Global Foundry, to build some in Australia. There should be some program. But anyway, another story for another day.
It is. Well, there are people who are trying to explore how to do that.
Yeah.
But what we do have is a very good research foundry on campus, and that's where we've made all of our quantum bits up to this point. Yeah. And for the company, we'll be making quantum bits up to around about 9 or 10 quantum bits in the next 2 years, okay? And we're well on track for that.
Yeah.
But eventually, we simply can't get the repeatability in the university foundry, and that's why we have to go to commercial foundries that have the regularity and repeatability. Yeah. So in the laboratories that we have nearby, we also have a lot of cryogenic facilities where we've done all of the initial testing, proving out of the technology, generated something like over 30 papers in Nature and Science journals to prove the basic physics package of the technology. This laboratory behind me is one that we built with our initial Series A investment round 2 years ago. So we funded the construction. It's on UNSW campus, so the university, we pay rent effectively through the university's sharing the company. And it is in this lab that we will be developing the commercial quantum computers that we're looking to sell and provide access to. So at the moment, we have some of our first refrigerators already installed. We're performing experiments on them at the very moment on some of our prototype qubit devices. And we're just about to expand those cryogenic facilities. We just recently, just in the last week or so, announced a second investment round into the company of $15 million US, led by a firm called Quantination, which is a domiciled in France, but global. They're a specialist quantum technologies investment firm, and they identified us really as a company to invest in. So with that investment, we'll be procuring more cryogenic platforms to test the devices that are coming from our foundry partners overseas. And ultimately, we'll be building complete quantum systems capable of solving some of those problems that I talked about before.
And what's the time scale or time frame on when it will be commercialized? By the end of the decade?
We intend by 2028 to have a system that will be equally powerful to any of our competitors around the world in terms of numbers of qubits and processing power. Okay, so in a sense we started a bit late, but because of the ability to scale very rapidly with silicon and to make many qubits very quickly and repeatably, we've got a very clear roadmap to be able to essentially overtake our opposition around about 2028. At that point, we're looking at a quantum computer with many thousands of quantum bits on a chip, and those will be commercially available, either for sale as units or we can make them accessible via cloud.
Well, let's go and have a look.
Sure, let's go in.
Okay, so we're now in the lab. What are we looking at?
Okay, so here are two of the Dzurak dilution refrigerators where we operate our quantum computer devices. The one over on my right is currently actually running experiments. That's working on a device with up to 4 qubits. It's made locally. The device is made locally here on campus at UNSW, and it's performing what are called quantum entangling operations on those 4 qubits. The refrigerator on the left over here is currently open. It's not operating at the moment. We're just changing the devices. There's currently 3 devices mounted on this fridge, and we're about to measure those in the next day or so. It takes around about a day to cycle and cool the fridge down. So these refrigerators go down to very low temperatures. They go down to about 1/100th of a degree above absolute zero.
Wow.
So that's 10 millikelvin. It turns out that our qubits don't need to be quite that cold. We've shown that we're able to operate those qubits up at the 1 Kelvin level. Now, 1 Kelvin, still very cold for you and I, of course, but in terms of the actual electrons and the devices, it's actually a factor of 100 in temperature. So one way to think about it is that the surface of the Earth is 300 degrees Kelvin in the absolute Kelvin scale. The surface of the Sun is 4,500 degrees, right? So that's a factor of 15 times. Think about that as to the difference between the really low temperature stage and where we can operate our qubits. Now, the reason that this is important is it means that we can integrate conventional chips. I'm talking about just standard integrated circuits. We can put those at 1 Kelvin with our quantum bits, and this is really crucial in order to do all of the control and error correction for a quantum computing system. So a big part of what Dzurak is doing is designing the full system, not just the qubits, but all of the control electronics that uses classical CMOS transistors. So the beauty is we're using the foundries to make the qubits, but also all of the associated electronics that can operate at that temperature.
It'll be a quantum system on a chip.
Exactly. Well, it'll be a quantum system on a module.
On a module, yeah.
So you might be aware, some of your readers, listeners might be aware that the semiconductor industry is really moving towards a chiplet-based model, okay? Where you maybe have a slab of silicon with a lot of interconnects, and then you put separate chiplets on it that can perform different functions. So you might have one that is the memory device, one that's a processor, maybe a cache, maybe an input-output device, etc.
Graphics, neural processor.
Exactly. And that's really the type of module that we're developing at Dzurak. Something that's fully integrated but compact, and that essentially just sits on one of the plates of this refrigerator. So as you can see, these refrigerators are about the size of a person, and you can hear that sound, that pumping sound. That's pumping on helium gas.
Right.
Okay, and it's an endothermic process that cools it down to the low temperature. But effectively, with these closed cycle systems, you just press a button, it cools down, and you're away, and then it maintains that temperature for years ultimately. Definitely, if you want. Yeah. Okay, these are very reliable cryogenic systems. Yeah. So one way to think about these cryostats is a little bit like when you go into a data center and you see a rack about the size of a rack. Yeah. That's providing you with some a multiple bank of processors to perform a particular function. That's essentially what you've got in one of these units.
And obviously that means that these units are ready to go into data centers in the future and fit in with the rest of the infrastructure quite easily.
Very important point, because as I was saying before, a number of these other technologies I was talking about for qubits, like superconductors, ion traps and photonics, need enormous physical systems and an enormous amount of energy to operate. So you might put one of them inside a data center. We're looking at putting hundreds or even thousands of these quantum computers. And this is actually very, very important, because in order to do those design problems that I talked about, designing drugs, doing logistics schedules and so on, these aren't fast calculations. They will take minutes, some of them up to hours to calculate, right? It's a bit like doing a high performance computing calculation. These are very advanced. And so that means we don't just want one quantum computer, we want many of them in a data center if we're going to be able to have apps that we can routinely access. And so this is really the focus of Dzurak, to get our quantum computers as compact, as cheap, as reliable as possible. And
as scalable as possible.
Absolutely, absolutely.
Wonderful. Well, Andrew, that's fantastic. We're going to see more from you tonight with the speeches from the Minister and others. But thank you for sharing a little bit about what's happening at Dzurak.
No, it's a great pleasure. Thanks very much, Alex. I've enjoyed chatting.
Thank you.